Welcome back, everyone. Ready for another deep dive?
Always.
Today, we're going to get our hands dirty, so to speak. We're diving into the world of wastewater.
That's right. And how it connects to something you might not expect, public health.
Exactly. So we've got this super interesting scientific article all about how scientists are using wastewater surveillance to, well, keep our drinking water safe.
Yeah. And it's not just like regular sewage we're talking about here. It's about these uh, potable reuse systems, the ones that take wastewater and treat it to the point where it's actually drinkable.
Okay, so we're talking about turning what goes down the drain into something we can actually drink.
Seriously.
Seriously.
Yeah.
This article, it was written by Jarity, Papp, and Pexon, and they really dig into how scientists are using the stuff we've learned about SARS-CoV-2 and wastewater to figure out how to make those potable reuse systems even safer.
Okay, so they're using what we learned about COVID in wastewater to figure out how to make the water we drink safer.
Got it.
You got it. And they focused their research on southern Nevada. Yeah, they looked at data from 7 different treatment plants there to get like a real-world picture of how the virus behaves. And one thing they found was that grab samples, basically like a snapshot of the wastewater at a specific moment in time, they can show much higher peaks in virus concentration compared to composite samples, which are collected over a longer time.
So if we're only looking at the average over time, we might be missing those sudden, spikes.
Exactly.
That seems kind of important.
It is, especially for smaller, potable reuse systems. Like, imagine a small town versus a big city, right? If everyone in a small town gets sick at the same time, it's going to have a much bigger impact on resources than if the same thing happens spread out across a big city.
Makes sense.
And that's where those grab samples come in. They're giving us a much more accurate picture of what's actually happening in those smaller systems.
Interesting. So they're not just looking at SARS-CoV-2.
Right.
There are other things that can make us sick besides COVID.
Right. So they took things a step further and used that SARS-CoV-2 data to model the behavior of a hypothetical enteric virus, kind of similar to norovirus.
No, norovirus.
Yeah.
Not fun.
Not fun at all. So they were trying to see how these kinds of viruses, the ones that spread through, the fecal-oral route, might behave in a potable reuse system.
Okay, so they want to understand the risks even when we're not in a pandemic.
Exactly. And to do that, they created 2 different scenarios to model how the virus might behave in a water treatment plant.
2 scenarios. All right, what were they?
So in the first one, they used the full range of SARS-CoV-2 concentrations they observed in the wastewater.
Including those high peaks from the grab samples.
Including all of it.
Yeah.
And then in the second scenario, they kind of smoothed out the data. They removed that highest peak to make a flatter distribution, and then they added in some simulated occasional spikes to represent those sudden outbreaks we were talking about earlier.
So they were basically trying to understand what would happen if there was a sudden surge of the virus, like during an outbreak, compared to a more consistent lower level.
Yeah, that's a good way to put it. They wanted to see how this thing called pathogen peak averaging could impact how well those potable reuse systems actually work.
Hold on. Pathogen peak averaging. That sounds kind of complicated. What is that?
So as wastewater moves through the treatment process, it goes through all these different stages, right? And that naturally mixes and disperses the pathogens. It's kind of like
A roller coaster.
yeah, maybe not the best image, but imagine the roller coaster track represents the concentration of the virus over time. It has high peaks and low dips, just like the levels of the virus in the wastewater.
Okay, I think I'm following. So are you saying the treatment process is kind of like smoothing out the roller coaster track?
Yeah.
Making those peaks less extreme?
Yeah, exactly. That's what pathogen peak averaging is.
Okay, I think I get it.
But here's where things get a little more interesting. Yeah, so it might seem like smoothing out those peaks is a good thing, less chance of being exposed to a ton of the virus all at once, but it's not quite that straightforward.
Okay, so what's the catch?
Well, when you average out those peaks, you kind of end up raising the concentration at those lower levels. It's like if you took the top of a mountain and spread it out across the whole landscape, you might not have that big peak anymore, but the overall ground level is higher.
So instead of a few big bursts of the virus, it's more like a slightly higher level all the time.
Right, and to figure out what that actually means in a real water treatment plant, they simulated how different kinds of reactors affect the virus concentration.
Wait, back up a sec. What do you mean by reactors? Are you talking like nuclear reactors or something?
Oh, no. In this case, reactors are just different parts of a water treatment plant. Pipelines, tanks, primary clarifiers, things like that. Each one holds the water for a different amount of time. That's called the retention time.
So some parts of the treatment plant hold the water for longer than others.
Exactly, and that affects how much those peaks and valleys in the virus concentration get smoothed out.
Got it. So longer retention time, more averaging, shorter retention time, less averaging.
Mm,
Makes sense.
yeah.
But how do we know how risky this actually is? I mean, knowing the virus levels are going up and down is one thing, but how do we know if it's actually dangerous to drink the water?
That is the big question, right? And that's where they use this method called quantitative microbial risk assessment, or QMRA.
QMRA sounds intense.
It's a mouthful, but it's basically a way to figure out how risky different things are. Like, we know crossing a busy street without looking is riskier than using a crosswalk, or eating undercooked chicken is riskier than eating well-done steak. QMRA does the same thing for water, but instead of cars and bacteria, we're looking at tiny viruses.
So they used QMRA to see how likely someone would get sick from drinking the treated water, taking into account all that peak averaging stuff we've been talking about.
Yep. And here's where the results get really interesting. The impact of that peak averaging, whether it makes the water safer or riskier, actually depends on how you measure the risk.
Wait, what? How many ways are there to measure risk when it comes to water?
Well, they looked at two main ways per ingestion risk, and daily or annual risk per ingestion risk is like the chance of getting sick from each individual sip of water.
So just focusing on that one gulp.
Right. And what they found is that the per ingestion risk is actually often higher when you have more of that averaging. Remember how we talked about spreading out the top of the mountain? Well, that means each sip has a slightly higher baseline level of the virus, even if those really high peaks are gone.
So each individual sip might be a little riskier?
Mm.
But what about over a longer period?
That's where daily or annual risk comes in. It measures the overall chance of getting sick over a day or a year. And those risks can actually be lower with averaging, especially in scenarios where you have those sudden spikes in virus concentration.
So even though each sip is a little riskier, you're less likely to get sick over a day or a year because the really high peaks have been smoothed out.
You got it. It's a complex trade-off, and it really challenges how we usually think about risk in these potable reuse systems.
This is making my head spin a little. It's like every piece of the puzzle changes the whole picture.
Mm.
So what does this all mean for regular people like me who just want to turn on the tap and drink some water without worrying about it?
Well, it means we need to be really thoughtful about how we design and manage these potable reuse systems. It's not just about getting rid of all the bad stuff. It's about understanding how it behaves and how different factors like retention time and this peak averaging can change the risk.
So we can't just say, get rid of all the viruses. We need to understand how they move through the whole system.
Exactly. And this has big implications for how we regulate these systems, too. Maybe we need to move away from strict rules based on the worst-case scenario and think about a more flexible approach that considers all these nuances.
So instead of assuming the virus level is always at its highest, we could take a more balanced approach that looks at how the treatment process actually affects those peaks and valleys.
Right. It's about finding the right balance between minimizing those really high peaks and keeping the overall baseline risk as low as possible. It's tricky, but it's super important for making sure the water is safe.
Wow, this is making me appreciate all the work that goes into keeping our water safe. So they were looking at viruses like SARS-CoV-2 and norovirus, but I'm guessing this could apply to other things too, right?
Oh, absolutely. This was just one study, but the findings are really important for understanding how we assess and manage risk for all kinds of stuff in our water. It's like a roadmap for future research, a challenge to dig deeper into how those tiny pathogens behave in these systems.
It's amazing how much we can learn from something most people just flush and forget about.
You never know where the next big discovery will come from. Sometimes the most unexpected places are the most interesting.
This is really fascinating stuff. Before we wrap up, I want to touch on that peak averaging thing again. It seems like a really important idea to remember from all this.
Definitely. It's a tricky one. Trying to balance out those high peaks and low dips in the virus levels and how the treatment process changes them.
And it's not as simple as just saying lower peaks are better, right? There's more to it than that.
Right. It's like a trade-off. You reduce those really high peaks, but then you slightly increase the levels at the lower end. It's all about finding that sweet spot to minimize the overall risk.
You mentioned earlier that maybe we need to rethink how we regulate these potable reuse systems. Could you talk a little more about that?
Sure. So right now, regulations often focus on those worst-case scenarios, like the highest possible level of the virus. But based on this research, maybe we should be thinking about it differently.
So maybe instead of just looking at that highest level, we could consider the whole picture, those peaks and valleys and how the treatment process smooths them out.
Yeah, exactly. We could have a system that's a little more flexible and takes into account the averaging effect and how it affects the overall risk. Maybe that could help us come up with better ways to treat the water that are more efficient and cost-effective, but still keep everything safe.
That makes a lot of sense. But I imagine it's not easy to change how these things are regulated.
It's definitely not simple. There are so many people involved, scientists, engineers, policymakers, and of course the public. Everyone needs to be part of the conversation.
One of the big takeaways for me is that we need to really think carefully about how we approach potable reuse. It's not just about getting rid of all the bad stuff, it's also about how it behaves and managing the risk and designing systems that can handle different situations.
I think that's a great point. This research is a reminder that we need to keep innovating and working together and keep pushing the boundaries of what we can do with water management.
It's pretty amazing how much we're learning about something that most people just take for granted. It's like a whole hidden world down there.
Yeah. You never know where the next big discovery will come from. Sometimes the most unexpected places turn out to be the most fascinating.
Well said. On that note, I think it's time for us to come up for air from this deep dive. Thanks for joining us as we explore this connection between wastewater and public health. And remember, even though it may not be the most glamorous topic, it's something that affects all of us. So stay curious, keep learning, and let's all work together to make sure everyone has safe and clean water for years to come.